Welcome to Complex Analysis Lesson 6 on limits. I assume the listener has taken a calculus course and is familiar with the limits of real valued functions. I'll give a quick example at the beginning just to refresh your memory, but the focus here is going to be on complex limits. We'll define those, we'll prove some theorems, we'll do a few examples, and we're going to need this for future lectures concerning continuity and derivatives. Okay, let's start with an example of a limit of a real valued function. We have it drawn here on the right. It's a step function. It's defined here. When x is greater than 0, the function is 1, this line here. When x is less than 0, the function is defined to be minus 1. When x is 0, the function is defined to be 0. For the limit to exist, the function on either side of the point of interest, in this case x of 0, needs to be the same. So we see that's not the case. The limit from the right is 1. The limit from the left is minus 1. And so the limit of f of x, this function here, does not exist at x equals 0. It does exist at all the other points, but not at x equals 0. And I'm just showing here a little bit more formally how the limit is violated based on the definition of a limit, which says that whenever, for a given point, in this case 0, whenever x minus 0 is less than epsilon, in other words, whenever you're within some given distance away from our point of interest, which is 0, then the f of x minus f of 0, which is 0, needs to be less than any value of epsilon. And if you pick, say, epsilon equal 1/3, then no matter how small you make delta here, you're going to, if for an x that's just slightly bigger than 0, you're going to get 1, which is not less than 1/3. If you're just slightly less than 0, you're going to get minus 1 and take the absolute value, it's 1 again. And that, again, is not going to be less than 1/3. So based on the definition of a limit, we also see that the limit does not exist here. In contrast to our first example, when you have a complex function, the limit needs to exist from all directions. So we only had left and right for the real valued function, but for a complex function, you can come from the imaginary axis, the real axis, the positive real axis. You can come from this direction, you can come from that direction, come from here. No matter what direction you approach your point of interest where you're taking the limit, it has to be the same value. So what I'm showing here graphically is sort of the issue. And this makes things a bit more complicated for complex functions. So we're going to look at a particular example. F of z equals z divided by the conjugate of z. And in the next slide, we'll show if you approach 0 from the imaginary, positive imaginary axis, you'll get one value. And if you approach from the positive real axis, you'll get another value. And since the two are different, we conclude the limit at 0 does not exist. So continuing with our function from the previous slide, we want to take the limit as z approaches 0 of this function I put up here in the upper right, just to remind us of what we're working on. We start by taking the limit as x approaches 0 from the positive real axis here. So we set y equal to 0, and we just let x approach 0 this way here. So we plug in y equals 0 into our function. Then we have x divided by x, which is 1. We take the limit, and we just get 1. Then we hold x equal to 0, and we approach the point 0 along the positive imaginary axis. We plug 0 in for x. We take the limit as y approaches 0, and we get iy divided by minus iy, which gives us, when we take the limit, minus 1. And so these two are different, which means the limit of this function does not exist as we approach 0. The definition of a complex limit at a particular point. So we have the limit as z approaches z sub 0, that's our point of interest, of f of z equals w sub 0, means that the f of z can be made arbitrarily close to the value w0 if we choose z close enough to the point z sub 0, but distinct from it. More formally, we can define the limit in terms of inequalities. The limit of f of z equals w sub 0 as z approaches z sub 0 if for each positive real number epsilon there is a positive real number delta such the modulus, basically the distance between f of z and w sub 0 is less than epsilon whenever the distance between z and z sub 0 is less than epsilon. So a little bit hard to take in. You might want to stare at that for a bit. I'm going to try to do it visually on the next slide. But the main idea here is that as z becomes closer to z0, the function is kind of squeezed as we get closer and closer to this value w sub 0. Okay, so here we'll try again our definition. Maybe this is a little bit easier to take in. So using some fancy notation here, for every epsilon, this means for every epsilon greater than 0, there exists delta greater than 0 such that whenever z minus z, the modulus of z minus z sub 0 is less than delta greater than 0. So in other words, whenever z is in this disk, anywhere inside of this disk, then f of z is inside of this disk, which has radius epsilon. So let's say it again. When z is in the disk of radius delta, the associated function f of z is necessarily in the disk about w sub 0 of radius epsilon. All right, we have our first theorem. Limits are unique. So if we have a limit of f of z as z approaches 0 and we assume it equals these values here, w0 and w1, then the two values have to be the same. The way to prove that is we'll take an epsilon divided by 2 greater than 0, and by the definition of limit, there exist these two deltas, delta sub 0 and delta sub 1, which give us these two expressions, these two statements here. It's basically the definition of this limit and this limit using epsilon over 2 instead of the usual epsilon. So both of these are true if we assume these limits exist. So we choose delta to be the minimum of these two, we choose delta to be the minimum of these two deltas here. So in other words, both of these conditions hold true. And then if these both hold true, what we have is that w sub 0 minus w sub 1 is less than or equal to, I've just added in the f of z and subtracted the f of z, so I left out one step here, but this would be less than or equal to, using the triangle inequality, f of z minus w sub 0 plus f of z minus w sub 1, but under the condition that these two things hold true, these two inequalities hold true, then we have this is less than epsilon over 2, the second term in the expression is less than epsilon over 2, the whole thing is less than epsilon, and since epsilon can be made arbitrarily small, we're forced to conclude that w sub 0 equals w sub 1. Okay, let's do an example. Let's show that as z approaches z sub 0, which could be any complex number of the function z squared, we get z sub 0 squared. And that looks kind of obvious, right? You're just plugging in z sub 0 for z squared. The proof is not all that easy, however. So given an epsilon greater than 0, we need to find a delta greater than 0 such that the modulus of z squared minus z sub 0 squared is less than epsilon whenever the modulus of z minus z sub 0 is less than delta and greater than 0. So we start by assuming delta is less than or equal to 1, and we have this expression here, z squared minus z sub 0 squared. We can factor that, it equals this product, and then since z minus z sub 0 is less than delta, we can just plug that in. So we replace the first term by delta. The second term you can write z sub 0 as minus z sub 0 plus 2z sub 0. And then using the triangle inequality, this term here is less than these two moduli here. And then we can go back, and since we assume delta was less than or equal to 1, that means z sub 0 is less than 1. We plug that in here, and we get this expression. So z squared minus z sub 0 squared is less than delta plus 1 times 2 times the modulus of z sub 0. And what we do is we let delta equal the minimum of 1 and epsilon divided by 1 plus 2 times the modulus of z sub 0. And whenever you take the minimum of two terms, you're less than either one of them. You're less than or equal to either one of them. So delta is less than 1 if we define it this way, which means that this is true, which means this whole expression here is true. And delta is also less than or equal to epsilon divided by 1 plus 2 times the modulus of z sub 0. So we could plug that into here, and then when we multiply, we get epsilon. So whenever the modulus of z minus z sub 0 is less than epsilon, we know that the modulus of z squared minus z sub 0 squared is less than epsilon, which is what we want it in order to prove our theorem. So that's quite a bit. You might want to pause the video here and just look at it a second time. The trick is to set delta less than 1, get an inequality here, then take delta to be the minimum of the reciprocal of this part of the inequality, and then recognize that whenever you set something equal to the minimum, it's less than or equal to both of the two things you have in here, and then the proof follows from there. In the second example, we're going to show that the limit as z approaches 1 of I times the conjugate of z equals I. We first take the modulus of f of z minus I. We plug in f of z here. You notice we have an I in both terms. We can factor that out. The modulus of I is 1. And then we have the modulus of the conjugate of z minus 1. I did a little bit of calculation down here. You can see that this modulus here of the conjugate of z minus 1 is the same as the modulus of z minus 1. So we just plugged it in up here. And so we have this expression. Now we take and prove the limit exists. We just take epsilon greater than 0. And then we note that whenever z minus 1 is less than delta, and we let our delta equal epsilon, then from this expression up here, if delta is equal to epsilon, then z minus 1 is less than epsilon, but we have that f of z minus I is equal to z minus 1, so when this is at less than epsilon, we have this expression here, which is what we wanted to prove. The following theorem gives us a way of simplifying finding the limit of a complex function. Basically, we break the function up, f of z, which is complex, into two real valued functions of two variables. We have u of xy, and then v of xy is the imaginary part. And the theorem is basically this: if the limit of f of z as z approaches 0 equals some value w sub 0, that happens if and only if the two limits for the real part and the imaginary part also exist and equal u sub 0, which is the whole thing. U sub 0 is the real part of w sub 0, and v sub 0 is the imaginary part of w sub 0. And I'm not going to do the proof here. It's a bit long and tedious. It's Theorem 1 of section 16 in the book by Brown and Churchill, which is one of the books I recommend to read along with in conjunction with this YouTube video series. Okay, using the theorem from the previous slide, we can prove this theorem here, which again, I'm not going to go into the details of, but it's very similar to what's done for real variables. You have the limit of a constant times a function is just that constant times the limit of the function. You can do the limit of a sum of two functions is the limit of the individual functions separately. Same thing with the product. The limit of the product is the product of each of the separate limits, and the same thing with the quotient, except you have the restriction that the denominator does not have a limit of 0, in which case the limit may not exist. On this slide, we have another theorem concerning a polynomial, complex polynomial in general form, which I'm showing here. The limit always exists, regardless of what particular value you're approaching. It's just a matter of plugging in the value, in this case z sub 0, into the function, and that gives you the limit. It's pretty much what you have from calculus for real valued functions. You have the same thing here. I'll just give you a very high level proof, or at least a sketch of a proof. The idea is that we first note that for a constant function f of z equals c, and the identity function f of z equals z, which are just special cases of this, the limit exists at every point z in the complex plane. And you can do that using the definition of limit. I won't do it here. It's very straightforward. Once you do that, then you can build up to more complex cases, because from the previous slide we had this theorem, which I kind of just summarized on the bottom here. So once you know that these two limits exist for a constant and for z, then you have in this case a1z here. That limit exists from this part of the theorem, and then you can add these two together and know that that limit exists from this part of the theorem in the previous slide. And then you just progress. You can get that the limit of z squared exists from the product rule here, and then you can get z cubed also, and then you just have a constant times z squared or z cubed, and slowly you build up the entire function here. So it's kind of very much dependent on the theorem from the previous slide, and it is useful because you don't want to keep going back to the definition of a limit every time you have a different type of polynomial, whether it's 3x cubed plus 7i. You don't want to use the definition of a limit to prove that the limit exists for all values of z. You just go back to this theorem here. Okay, so far we've been talking about the limit approaching a given complex number. We haven't talked about the limit as z approaches infinity. We know from calculus that that's quite common, that you have a x approaching infinity, and sometimes the limit does exist. For example, the limit of 1 over x as x approaches infinity is 0. So what we need to do first, before we talk about that, is to extend the complex plane to include what's called the point of infinity. And the way that's done is through the what's called the Riemann sphere. I took the definition here from Wikipedia. Let me just kind of read it quickly. The Riemann sphere, named after the famous mathematician Bernard Riemann, is a model of the extended complex plane, also called the closed complex plane. It's basically all the complex numbers plus one point at infinity. This extended plane represents the extended complex numbers, that is the complex numbers plus the value infinity. With the Riemann model, the point infinity is near to very large numbers, just as the point 0 is near to very small numbers. So that's the Riemann sphere. The reference here in Wikipedia will give you a little bit more information. I'm going to go through some further details on the next slide. Okay, here's a picture of the Riemann sphere. There's a lot on this slide, so just kind of take a deep breath and let me explain one piece of it at a time. And some of the pieces actually are not needed for the discussion at hand. And to give a reference here, this is from the Wikipedia article I mentioned in the previous slide. So the grid here was the C, that's the complex plane. And then we have this sphere. You can think of it as having radius 1, although I guess the radius really isn't critical. Let's just say it has radius 1. And it's kind of split between in half by the complex plane. Now what we want to illustrate here is that every point on the complex plane has a unique point on the sphere, and every point on the sphere has a unique point in the complex plane. It's a one-to-one mapping. So we take a point A here that's outside of the intersection of the sphere with the complex plane, and we just draw it up all the way to the top of the sphere, and where we intersect the sphere, this point P of A is the unique point that's mapped to A from the sphere to A and vice versa. And that'll work for any point outside of the intersection of the sphere with the complex plane. Now if you're inside of the sphere here and on the plane, for example point B, then you do the same thing. You draw a line from the top of the sphere to B, but then you don't intersect the sphere until you hit the lower hemisphere. And you see here that B has its unique point on the sphere P of B, and that's true for any point in this gray area here. So, and then of course if you're on the boundary, the point on the complex plane and the point on the sphere coincide. So all that together gives you one-to-one mapping, except for the point at the very top here. That doesn't map to anything because if you actually, there's no line from the complex plane that hits this, except if you define this point at infinity. So if you take some point that's infinitely in the distance in any direction you choose, that maps to this P of infinity, and that's the mapping that we use to extend the complex plane to include the point at infinity. We have three different cases concerning the point at infinity. I'll go through each one of those and define what it means and then give an example. So the first case is where z approaches z sub 0 for a given function and the value goes off to infinity. In terms of the formal definition, it's what we have here. For every epsilon greater than 0, there exists a delta greater than 0 such that the modulus of f of z is greater than 1 over epsilon whenever the modulus of z minus z sub 0 is less than delta and greater than 0. The idea is that you can take epsilon as small as you like, and f of z will always be bigger than that given some disk about z sub 0. And that's equivalent to the limit of z approaching z sub 0 of 1 over f of z equals 0. Sometimes it's easier to evaluate this as opposed to this. And so I have an example here. taking the limit as z approaches I of z plus I over z minus I. It goes off to infinity, and the reason for that is that if you take the limit of 1 over f of z, which is basically just flipping the numerator and the denominator here, and you put in z equals I, the top is 0 and the bottom is 2I, and that equals 0. So using this equivalent definition, we can say that this limit goes off to infinity. In the second case, we take the limit as z approaches infinity, and we actually get a finite value. That's possible. And the definition of limit, again, needs to be modified a little bit. I'll read it off to you here, but I think the equivalent definition is more useful. But in any event, I'll read off the formal definition. For each epsilon greater than 0, there exists a delta greater than 0 such that f of z minus w sub 0, the modulus of that, is less than epsilon whenever the modulus of z is greater than 1 over delta. And that's equivalent to the limit as z approaches 0 of f of 1 over z equals w0. So let's take a look at an example. So we have here the limit as z approaches infinity of 3z plus 2I over 5z minus I equals 3/5. And the way we get that is we use this equivalence here. We put in 1 over z for z. We get what you see here. Then you multiply top and bottom by z, and you get the limit as z approaches 0 of 3 plus 2iz over 5 minus iz. And when you put in z equals 0, this and this cancel to 0, and you get 3/5. Okay, in case number 3, this is when things kind of blow up, and you have the limit as z goes to infinity of f of z actually goes off to infinity. That's usually a case which is excluded or written off as not being helpful, but you still need to know when that happens. So the technical definition in terms of limits we have here: for every epsilon greater than 0, there exists a delta greater than 0 such that the modulus of f of z is greater than 1 over epsilon whenever the modulus of z is greater than 1 over delta. And that's equivalent to the limit, this limit here is equivalent to this, the limit as z approaches 0 of 1 over f of 1 over z equaling 0. So we have an example. The limit as z approaches infinity of z to the 4th plus z over z cubed plus 1 equals infinity. And then using the equivalence, we put in 1 over, first of all, we invert it, and then we put in 1 over z for z. And you see here we have 1 over z cubed plus 1. So this is putting the denominator in the numerator, and then putting in 1 over z, and then putting in 1 over z to the 4th plus 1 over z. We multiply the top and the bottom by the highest power that's present, which is z to the 4th. So we get, on top we get z plus z to the 4th. On the bottom, this just becomes 1 plus z cubed. Then we put in z equals 0, and you get 0 plus 0 over 1 plus 0, and that equals 0. And you kind of guessed that was going to be the case because you have a higher power of z here and a lower power on the bottom. And you would expect that to go off to infinity, and in fact it does using this equivalence.